class of Control System 1. I am Srianjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this class, we will discuss about the stability concept and the determination of stability by using the pole locations. My slide contains the stability, the classification of stability, the Bibo stability, the stability criteria, S-plane, location of poles, and the stability depending on the location of poles. Now, what is the stability? Actually, in designing of a control system, the main objective of a control system engineer is that the design system must be stable when it is subjected to command signal or any other disturbances in a loop and change the parameter of the feedback loop. Now, stability is a very important characteristic of any system, and it implies that small change in input do not result in large effects on the system response. That means if small perturbation arises in the system input or the initial conditions, a stable system will present the small modification in its perturbed response. But if it is applicable for the unstable system, then the outputs go unbounded or until the system disintegrates. And stability is the basic requirement of a dynamic system that performs operations or process signals. Now, this is an example of stable signal and another is unstable. So, if any other disturbances is present in this stable signal, if the system is stable, then the output will remain unchanged. That means there is no perturbation will be affect the output. Whereas if the system is unstable due to the perturbation, the output will go unbounded like this. Next is the classification of stability. Basically, the stability can be classified as the input-output stability or the asymptotic stability. Now, there are two responses in a system. One is zero set response and another is zero input response. And for the zero set response, we have considered the input only, whether the initial conditions are zero. And for the input response, that is input is zero because the name is the zero input response, whereas the input is zero, but the initial conditions are there. So there are two types of stability according to two responses. One is input-output stability, and this stability is known as the Bibo stability, that is bounded input, bounded output stability. And here we are assuming that all the initial conditions are zero and only the inputs are acting on the system. And stability of the response to inputs only is calculated. And in case of internal stability or the zero input response stability, the given input is zero, and due to the initial conditions there will be some response, and that stability is known as the asymptotic stability. So in this slide we will consider the Bibo stability. So Bibo means bounded input, bounded output stability, and these are the examples of bounded signal. Now bounded signal means it will bounded within this margin. So if we consider this exponential decaying function, then this signal is bounded within this peak value to the value 0, because it decays to 0 with respect to time t, as well as if we consider this function, then it's bounded within the magnitude a, and it is continuously remaining a when the t is increasing. That means in both these cases the signal is bounded within a marginal value. So here it is less than the BU, that is the boundary, when k is equal to 0, 1, 2, etc. That means this value is bounded within this 0 to any fixed value. And the unbounded means the output or the input, whatever it is, that will be increases with respect to t. That means if t increases, it goes unbounded condition. That means there is no boundary within this response. So these two can be used as the bounded input as an example, and this can be used an example of unbounded input or unbounded output. Now, if we consider a system GS is the transfer function, whereas GT is the impulse response due to the RS, CS is produced. So we can write down the CS is equal to GS divided by RS from this system. Now, if applying the convolution property of Laplace transform, we can write down that Ct equal to integration 0 to infinite g tau rt minus tau d tau. Now, if rt is bounded such that this rt is less than or equal to m less than or equal to infinite, the magnitude of output can be expressed as then Ct mod of Ct equal to mod of this integration equation, or it is less than this integration, that's less than equal to m into integration of 0 to infinite g tau d tau. So the output is unbounded during this condition, integration of 0 to infinity mod of g tau d tau less than infinite. So we can conclude that the system is Debye stable if and only if the impulse response is absolutely integrable. And if a system is given as a bounded input and it is produced the bounded output, then system will said to be Debye stable system. Now, GS is the Laplace transform of GT, so we can find out the condition for stability in frequency domain also. That is, depending upon the pole locations and zeros locations in the S plane. So next, what is S plane? Actually, S is a complex variable and it is defined as S is equal to sigma plus j omega, where sigma is the real part of S and omega is the imaginary part of the S. Now, consider this plane, that is the sigma plane and sigma and j omega axis, and this plane is known as the S plane. This horizontal axis of the S plane is known as the real axis, or it is represented by the sigma. And here all the imaginary values are 0. So all omega values are 0. So S is equal to sigma in the real axis, and the vertical axis is known as the imaginary axis. This j omega axis is the imaginary axis, and in j omega axis all the real values are 0. So in this axis, S is equal to only j omega, and this is the origin, and origin can be represented as 0, j0, or the 0, and the region to the right of the imaginary axis, that is from 0 to plus infinite, that is the right half plane, that is the whole plane from this to infinite, and for the region to the left of this imaginary axis, that is this one from 0 to minus infinity, that is known as the left half plane. And the poles in this plane, and look according to that pole location, we can determine the stability of the system. Now, let us check how the pole locations are depending on the stability of the system. So, let us consider the different location of poles. So, first we can consider all the poles are real, and real poles are located at first one on the left hand side. So, this is a real pole that is located on the left hand side at minus a position. So, if it is at minus a position, then the transfer function becomes a by s plus a. Now, if we obtain the impulse response, then the Laplace inverse of this a by s plus a becomes a into e to the power minus at. Now, this output response is impulse response is exponentially decaying function. So, as it is exponentially decaying function, so that we can say that it is bounded within this region. If it is a, if t is equal to 0, then e to the power minus 1, that is only a, so it is bounded within a to 0. So, due to this in pole location, the output is, if a pole is located at minus a, the impulse response model, we get the output as the exponentially decaying function, and hence the system is called stable. So next is the pole is located in the right half of the S plane, and pole is the real pole. So if the pole is real pole and it is located at plus a position, then we can say the transfer function is a by s minus a. And if we plot the impulse response model, then we will get a to the power at according to the inverse Laplace formula. So it is an exponential increasing function. So we cannot say that if t is infinite, the value will go infinite. So we cannot say that it is bounded. And if it is unbounded, then the system will be unstable. Next is the pole is located at 0, 0 position or at the origin. Now, in this case, pole is located at the origin, so the transfer function can be denoted by a by s, and when it is a by s, the inverse Laplace is um, only a, that is, if t increases, then the response is a constant value. So, this is the marginally stable condition. Next is the complex conjugate pole. So first consider the complex conjugate pole is located at the left half of S plane. Now when the pole is located at the left half of S plane, so we can say that its position is A plus JB and its position is A minus of JB. So the transfer function can be written as like this: A by S plus A plus JB plus A star by S plus A minus JB. Now the impulse response model can be found out in this way. It is 2a to the power minus 18 sin dt plus 90. So it is an exponentially decaying function. So it is exponentially decaying and it is a damped sinusoidal response. So it is bounded within this limit to zero limit, because if t is increasing, it is going to almost zero. So it is bounded output. So this due to the pole locations at complex conjugate poles at left hand of this plane, the system will be stable. Next, we will consider the poles located at the right hand side of the S plane and both the poles at the complex conjugate poles. So if we find out the impulse response, then we will get e to the power 80 into cos dt, the sin dt plus 90 degrees. So it is exponentially increasing function, because when t goes to infinite, then it can be infinite. So it is not bounded. Hence, we can say these pole locations are, if the poles are located at the right hand side of the omega axis and all the poles at the complex conjugate poles, then the system is unstable. And next, we'll consider the both the poles are located on the j omega axis, and if these poles are located at j omega axis, then the 0 plus minus jb, and the transfer function becomes a by s plus jb plus a at by s minus jb, and impulse response model is 2a cos dt, and that is oscillatory response. That means it is again marginally stable. And the next one, that is multiple roots located on the imaginary axis. That means in a single location there are two poles is located here, and here also two different poles are located in the same location. So we can write this transfer function like this: 0 plus jb whole square, and the transfer function is, can be written as a by s plus jb whole square plus a dash by s minus jb whole square. Here the sigma part is 0 because both are located on the imaginary axis, so there is no real values. And if we calculate the impulse response, then we can write down this 280 into cos dt. And if you plot this, ct looks like this, and actually this response is the unstable response because it is not bounded within the region. So we can say that if all the roots of the characteristic equation, that may be the real poles or the imaginary poles, left in the left half of S plane, then the system is stable. If any one of the roots, that is of the characteristic equation, lies in the right half of the S plane, then the system is unstable. And all the roots lie in the left hand side of the S plane, and one or more non-repeated roots are located on j omega axis, then the system is marginally stable. And if the characteristic equation has repeated roots on j omega axis, then the system is unstable. Next, take an example. Transfer function is given as gs by k by s square plus 1 whole square into s plus 1. So this is a characteristic equation, and we can find out the pole locations as plus 1 plus k. There are two poles at the plus j position and two poles at minus j position. So total 5 number of poles. So this is minus 1 pole, and pole is denoted by the cross line, and zeros are located on the circle. And there are two poles at plus j location and minus j location. As there are two poles, there is a repeated root on j omega axis, and the system will be unstable. So in this way, we can check the stability of the system by finding out the pole locations of the system. These are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.